Okay, welcome to Crapload of Examples. We're doing integration by substitution today. Uh, Same with the last video, I'm not going to go into the theory of it. Suffice it to say it's the chain rule with an integral on both sides. Um, I'm going to start out with a strategy session, sort of like we did before. Just kind of talking about why you would want to use this and also how you're going to kind of think about these problems as you see them. Integration is a little bit different. These techniques are a little bit different than some of the things you might have learned in Calculus 1, in that you're going to have to apply a little bit of creativity to get to the final goal. So this is the basic integration by substitution. Oh, and before I continue, I should just say if you want to see examples, they should be time-stamped in the description, so just go right ahead. But this is the basic formula for integration by substitution. Again, it's closely related to the chain rule. What you're going to get is one of a couple types of integrals, okay? The first kind that you're going to see is something like this, all right? I'm just going to give you just an example, okay? We're going to do something very similar to this one in just a few minutes. This is the kind of thing that you might see right off the bat. Okay, what you're looking for when you see an integral, if you're not sure whether you should use integration by substitution, you're looking for a function within a function. That's a big part of it. A function within a function. That's a dead giveaway that you should be thinking about substitution. So that's the first thing to look for. Function within function. And the function that's inside is going to be your candidate for u, okay? So this one is going to be your u, and this one is going to be f, okay? And so the way that we're going to try to rewrite this is in terms of u, and then we're literally going to integrate by u. That's the whole trick, okay? And you'll see what I mean here in a second. The second thing that you're going to be looking for after you've sort of seen this function within a function and you've found the one that's inside the other function. So in this case, u is the one that's inside the function u to the fifth. Okay, u is going to be 1 plus x squared. And this function, this f, this broader function here, this is going to be f of u is u to the fifth, okay? Take a second and make sure you understand what I'm saying here. If you can imagine plugging in u, which is defined as 1 plus x squared, into this, you would get 1 plus x squared quantity to the fifth, which is what we're talking about here. So this is f of u. The next thing you're going to want to try to find is the derivative of u in the integral. Okay? Or I suppose the more proper way to say that is in the integrand. And as you can see, what's the derivative of u? Well, du dx is 2x. I think I see a 2x here. There you go. Bada bing, bada boom. Now, there is one notational point to make here. Most of the time, because you're going to be integrating by u, what you'll do is you'll kind of move this dx over to the other side. Okay? And this is going to look like this. And the reason you do this is because you're literally replacing everything in the integral. Okay? You are substituting everything in the integral, including this cumbersome dx that can be a little puzzling at times. All right? Once you've done that, once you've located these things, you're going to fill in the formula. Okay, and so let's go ahead and do that on the other side here. I've got my u, I know my u, I know my du, right? And I know my f of u, so here we go. Integral of f of u, u to the fifth, with respect to u, that is just going to be u to the sixth over 6. And I'm almost done. That's as simple as it gets, really, on some of these. The last thing you're going to want to do is plug u of x back into your answer. So the answer is in the same indeterminate as before. We'll say x in this case. It needs to be the same indeterminate that you had to begin with. So x was what we had to begin with. We need to change u into x again. So how do we do this? Well, we plug in 1 plus x squared. 1 plus x squared. And that's going to be to the 6th over 6 plus c. And I'm done. That's as simple as it gets. So you're starting with this integral you don't know. You identify a function within a function. You call the inside function u, and then you try to find its derivative. Then you can rewrite the whole thing in terms of u. A lot of times what you'll see is something like this. Okay, let's just do the same thing. This is very similar to this integral, right? And I would go about this, I'd start out by finding my function within a function, just as I did before. So this is my f of u, and here is my u. Okay, and this is going to be u to the 5th, and u is going to be 1 plus x squared, right? But here, the derivative of, if I write it out like I did before with the du and then a dx on the end, the derivative here is 2x. Well, I only have 1x. So what I'm going to have to do in that case is I'm going to have to introduce another unit constant just to make sure my derivative is replaceable. Everything is replaceable, but I've got to make sure I'm replacing exactly the same thing. Otherwise, this just doesn't work. So really brief strategy session there, and let's go ahead and get into it. Okay, here's our first integral. It's very similar to the one we just did in the strategy session if you looked at that. So we're going to first identify the function within a function here. Okay, and we can say that u is the inside function, that's x squared plus 2. The outside function f of u is going to be u to the 3rd. And then we need the derivative of this with the dx on this side. Okay, so the derivative of u is the derivative of x squared plus 2. That's just 2x. And now we see that here. One part of it is here. The other part of it is here. So we can go ahead and rewrite this integral with a du. Okay, and now we need f of u, which is u cubed. And we're integrating with respect to u. So this is just u to the 4th over 4 plus c. But what do we have to do? We have to turn it back into our original indeterminate. So we have to plug back in x squared plus 2 into u. And this is our answer. Okay, here's another example. Very similar to the last one. Here's our function within a function. We have u here. U is going to be x cubed plus 1. Our f of u is going to be u to the 7th. Okay, so let's go ahead and write these things out. F of u is u to the 7th. U is going to be x cubed plus 1. Du is going to be the derivative of this with this dx over here. That's going to be 3x squared. The derivative of x cubed plus 1 is just 3x squared. Well, look here. There's the first part. There's our dx. So we can rewrite this as f of u, which is u to the 7th, times du. Okay? And that's going to be u to the 8th over 8 plus c. When I said times, I didn't really mean to do that. I mean, we're integrating by u, so ignore that. If that confused you a little bit, I apologize. Now remember, we have to plug our u in the original indeterminate back into this u. It's not enough to just say it's u to the 8th over 8. We're going to need to make sure this is in terms of x's, because that's what we were asked. And this is your integral. Okay, one more here before we go on. Oops, I wanted to do a quick definite integral, okay, to show you what happens when we use substitution in definite integrals. So we're going to proceed as we have been, first identifying our function within a function. Okay, so here we have our f of u. That appears to be u to the 4th. U here is, of course, going to be x squared plus 1. Okay. Our du is going to be 2x dx, and of course that's because I'm taking the derivative of u and I'm making sure my dx is over here so that I can replace everything. Now, one thing you need to pay very close attention to is the bounds of integration. One second. The bounds of integration are going to be substituted as well. You're going to need to plug those bounds into the function. So sort of in the indefinite sense, right, what we were going to do is rewrite this as u, and then we were going to plug x with the x form of u, which would be x squared plus 1, back into u once we were done, sort of like the last couple of problems. What you're going to do in the definite case is you're going to go ahead and plug these into u, and when you write your integral, you're going to have new bounds of integration. I'll show you right now. Now, first of all, we have f of u, so we have u to the 4th here, okay? But we don't quite have our du. We're missing 2, okay? So what I'm going to do is I'm going to put a 2 here, and then I'm going to take it out of the front of the integral, okay? And obviously this constant would pass right into the integral and cancel with that 2, so this is totally fine to do. And I'm going to say this is 1/2. Now we have our du in the integral, so I can write it this way, and we figure out what our bounds of integration are. Quickly stating this, if we had ab, okay, this is going to go to u of b and u of a. So what is u of a? Well, that's going to be 0 squared plus 1. This is going to be square root of 2 squared plus 1. Look, see, this would be a, and I've plugged it into u. This is square root of 2, and I've plugged it into u to get my new bounds. So these are just going to be 1 and 3. I'm now going to go ahead and calculate this as if I would any other definite integral. This is u to the 5th over 5, and now I just need to use these bounds 1 and 3. And I have something that I'm going to pull this 5 over. 1/2 times 1/5 is 1/10. And this becomes 3 to the 5th minus 1 to the 5th, which is just 1. And I'm not going to bother calculating that out. I think it's, what is that? That's 9 squared times 3, so 243. I guess I might as well. That's 242 over 10, or 121 over 5, or something like that. Anyway, so you get the idea. The biggest thing to note here is what you're doing with your bounds. I do want to point out, if you've done it the way that we were doing it before, don't get too confused, because, like I say, if you've done it the way that we were doing it before, and you went ahead and plugged in your u function here, okay, that would be x squared plus 1 over, to the 5th over 5. right? And then you took these original bounds, it would give you the same thing, okay? So whether you go about it this way or this way, by switching these bounds, it shouldn't matter. Don't freak out about it too much. But this is the way that they generally teach it, so it's probably best to go ahead and do it. Okay, so here's a slightly more interesting example. I have a function inside a function here. F of u is going to be e to the u, and my u is going to be x squared. Okay, so let's go ahead and write that out. I've got this down here already, so I'll just keep writing here. U is x squared. And again, if you plug in x squared, you get e to the x squared. That's what we're talking about, okay? Now du, again, 2x dx. I have an x dx. I need a 2x dx, so I'm going to go ahead and do that trick I did before, where I sort of just bring it in. Now I've got my full du here, and I can continue keeping that constant in front. So I've got my du, which was 2x dx in this integral, and I've got my e to the u, and of course the integral of e to the u is just e to the u plus c. Now we can't forget to make sure and go back into x's. That's what they wanted to begin with, so here we go. And that's our integral. Okay, another one here that's very similar to the one that we just did. We have our function inside of a function here, and I'll just put parentheses around this so I'm very clear. Here's our function inside of a function, so we have f of u is going to be sine of x. Oh, I'm sorry. Oh, I almost made a big boo-boo there. All right, here we go. Sine of u. Yes. And u, again, is x squared. Okay, so u is x squared. And du, again, is 2x dx. I hope you don't think these are too simple. They will get complicated in a minute. So again, we've got our fu here. We've got our u is x squared. We have most of our du again, so we're going to use that same trick. Going to take this 2 just so that I can get all of this du there. And now I have every piece of this ready, and I'm going to go ahead and rewrite the integral. This is sine of u du. And I know the integral of sine is minus cosine, so this is 1/2 minus 1/2 cosine u plus c. I put this x squared back into where the u is to make sure that I wind up with the same indeterminate that I had initially, and here is my integral. Okay, another one that's pretty easy, but also a little bit different. Here we don't have a function inside of a function as we did before, but this is maybe the first segue I have into what's called trigonometric substitution. Okay, what I'm going to do is I'm going to call one of these u. And it turns out in this case it doesn't really matter which one I call u. Okay, and here's why. Let's just pick sine, and then maybe I'll try it the other way. So let's say that u is sine of x. Okay, so here's my u. Then here's something else. I'm not naming that yet, but I do know that du is going to be cosine x dx. Well, look at this. That's du. So here I can rewrite this as the integral of u du. I'm going to take just a second to reflect on this, because this is, I mean, obviously we can continue this out. We know how to integrate that. Okay, and then that becomes plugging in sine x. That's sine x squared, or sine squared x, however you want to say it, plus c. But the point is, this is another way that you can use integration by substitution. If you notice something in the integral, and you see its derivative also in the integral, that's a dead giveaway that you should be looking at integration by substitution. Here, I knew that sine's derivative was cosine x, so the derivative of sine was also in the integral. This might be somewhat surprising to people, but you can also solve this integral by means of trigonometric identities. I believe 2 sine x cos x is sine 2x maybe, or something like that. I don't know, but yeah, I think it is. Anyway, bottom line, this is one way to solve this integral. Very neat, easy way to do it. Let's quickly try it the other way. Let's just see what happens if we do. If we didn't know what to do and we were freaking out, this just goes to show you that it's always best to at least try something. Okay, so let's try it with cosine instead. Okay, so let's pick cosine. Okay, well, the derivative of cosine is what? It's minus sine x dx. And so I have a negative sine x, but I have a positive sine x, but I need a negative one. So I'm going to put a negative sign here and then a negative sign in front of the integral, and I can rewrite this minus u du. And what does that get me? That gets me minus u squared over u plus c, which is minus cosine squared x over 2 plus c. I just want to point out very quickly that something sort of interesting happened there. Okay, so I have two different... Hang on. I just wanted to make note of this because this is something I haven't noticed before. What we just said is that this result with that integral and this result with that integral were the same, and if we actually subtract these two, what we get is 1/2 plus c. This would be absorbed as a closed form in c. So this is kind of an interesting thing, but I'm not going to dwell on that too far. Let's go ahead and get going with the next one. Okay, so here we're going to prove some kind of an identity, okay? Maybe if you were assigned to make a table of integrals, not that it's 1950 and people still do that, but this is just going to be a positive, or I guess we could say a natural number in, okay? And so here's the integral we have, and clearly we have this is a function within a function just like we had before, so our u is going to be cosine of x, and our f of u is going to be u to the n, all right, and the derivative of u is going to be sine x, minus sine x dx. So again, I'm missing a minus sign in front of that. I'm going to cobble together my du here, minus sine x dx, that's what I'm looking for. Okay, I'm going to keep the first minus sign because I can't get rid of that. And then I just have u to the n. Okay, and we're integrating, oh my lord, we're integrating by u here. I'm going to integrate by u. So this is minus u to the n plus 1 over n plus 1 plus c. And then we remember to get back to our original determinant. So we need to plug in cosine of x, cosine x to the n plus 1 over n plus 1 plus c, and that's our integral. Okay, here is a bit of a tricky one. So, let's think of how we can do this. What do we know about sine 4x? Okay, so the one way we could rewrite this is, okay, sine squared x squared. Now cosine to the 7th of x is going to be cosine to the 6th of x times cosine of x. All right, why am I doing this? I'm trying to isolate a bunch of sines, okay? So here we go. I'm going to Well, no, let's keep going and see what happens. Okay, so we now have sine squared x squared. What is cosine to the sixth of x? Well, it's 1 minus sine squared of x to the third. Why is that? Because 1 minus sine squared of x is cosine squared. Okay, so now we have this integral. So we have a polynomial of sines, and then we have cosine x. This is a function of u's, and this is its u's derivative. Okay, so here we go. This is our function now. F of u is u to the fourth, I should have just put to the fourth, times 1 minus u squared cubed. U is going to be sine of x, and du, as before, is going to be cosine x dx. So just to take a step back, this right here was unnecessary, what I did. Don't necessarily have to do this, okay? In fact, for the sake of clarity, I'm just going to remove this and pull it back to what it was before. This was in search of finding f of u, and I think we've done a decent job of that. But we still have this kind of spanky polynomial here that I'm not in love with. So how can we rewrite that? Well, we've got a u squared out here, and we also have a 1 minus u squared in here. We could just expand this, and maybe that's the smartest thing to do. So let's just try that. This u to the third, or cubic polynomials are not that hard. So here we go. Let's do this. Let's go 1 minus, this is going to be u squared. Hang on, let's just write this out. I remember it's 3, 3, and 1. You can kind of take your time with this if you want. I'm going to do a little bit of mental math, but if you expand it on your own, you'll get the same thing I did. So this is going to be minus u squared, and then here we're going to have a plus 3u to the fourth, and then we're going to have a minus u to the sixth. We're going to continue to distribute here, so that's u to the fourth minus 3u to the sixth plus 3u to the eighth minus u to the 10th. Good God. Okay, so here's our f of u, right? So let's just walk through this again. What did we do? Well, we pulled all of the signs out, all of the cosines out except for one, so that we could leave it as a derivative. Okay, and then we consolidated all the signs here. We wrote them as a function inside of a function, so the inside function here is sine, and then we're just calling all of these things u's, and now we have a polynomial of u, which we've expanded here, and now we can just integrate that. So this whole thing, again, we have our du here, very nice and neat. This is going to be our du, so now we've got f of u, which is u to the fourth minus 3u to the sixth, plus 3u to the eighth minus u to the 10th du. That's u to the fifth over 5 minus 3u to the seventh over 7 plus 3u to the ninth over 9 minus u to the 11th over 11 plus c. I'm going to make some space here. Okay, just cleaning this up a little bit. Why did I do that? Well, let's just remember that u was sine of x, okay? So here we go. We're just going to plug in sine of x everywhere we see a u. Good Lord, man. This is an unlucky problem. Here we go. And we can cancel that 3 if you want to. I may not even bother because this problem is super duper spanky. I'll do it, whatever. I'm going to cancel the 3 and just leave a third as the coefficient for this. Okay. And then finally sine x to the 11th over 11. That problem was wacky. But there you go. That's the answer. Okay, so I decided to go ahead and try another one of these. We'll do this one a lot more smoothly than the one before. Again, the whole point of this, when you get to these trigonometric ones, is identifying derivatives and functions as pairs inside the integrand, okay? And these you're going to see a lot of because sine x and cosine x, they relate with each other by derivatives. So here we go. We're going to start with this one, and we're going to see what we can get to, okay? The first thing I'm going to do is I'm going to take out this even power of sines. Why am I doing that? Well, just like the last time, I know that sine squared x is 1 minus cosine squared x, okay? So I can rewrite this as 1 minus cosine squared x squared, right? Because it's sine squared squared. That would get me 4. 2 times 2 is 4. So this is the same thing as this, all right? And now I have one last sine left over. Well, okay, here we go. Now we're talking. We have a nice function within a function here, okay? And what we really ought to do is just go ahead and leave that cosine as u, okay? So let's make cosine u, okay? Then du is going to be minus sine x dx. Well, what does that leave for f of u? Okay, f of u is going to be 1 minus u squared squared. Okay? And I think I'm going to need to, just like I did before, I'm going to need to expand this. It's the easiest way to get this problem done. That's just 1 minus 2u to the 4th plus u, I totally screwed that up, sorry, u squared plus u to the 4th, okay? These two things are the same. So here I've got my du here. I need a little minus in front because I have part of it, but I don't have this negative sign. So again, I've got to do that to my integral. Bring that out in front. And I have 1 minus 2u squared plus u to the 4th equals u minus 2u cubed over 3 plus u to the 5th over 5 plus c. Going to plug in my u in terms of x. So that's cosine x minus 2 cosine x quantity cubed over 3 plus cosine to the x to the 5th over 5 plus c. That's my integral. So let's just take a step back. What did we do? Okay, we took the even powers out. Why did we take the even powers of sine out? Because we can write them in terms of cosine. Why did we want to write them in terms of cosine? Because there's an extra sign, and the derivative of cosine is negative sine. So it left my du nice and neatly in the integral still, where I could write whatever I have with cosine in terms of a polynomial. This is my f of u, and so I was able to expand this f of u as a polynomial and just integrate over it. The one thing that I could have spent more time talking about was what I talked about earlier, where you need to make sure this du is exactly the same. Here I had positive sine x dx. Here I had negative sine x dx. I needed to fix those negative signs in order to make sure that this negative sign was inside the du, so that I could do my substitution in a correct way. Okay, here's one that you're likely to see some kind of problem sort of similar to. This requires some comfort with trigonometric identities, and it goes back to what I had said before when I did the integration by parts examples video, that if you're doing Calculus 2, having a cheat sheet of trigonometric identities will be worth its weight in gold, simply because you're going to run into them a lot. So in this case, we're going to remember that the derivative of tangent, okay, this is one of the things you're going to want. Trigonometric identities and also their derivatives to do this stuff. Okay, so the derivative of tangent is secant squared x. Okay, now you'll notice here I have two of those, right? I have two secant squared x's. But what I can also do is I also know that secant squared x, okay, what is secant squared x? I think we ran into this in integration by parts. That's 1 over cosine squared x, right? And tangent squared x is sine squared x over cosine squared x. These things precipitate from the definition of secant and tangent. Tangent is sine over cosine, secant is 1 over cosine. So if I subtract tangent x from secant squared x, I get cosine squared x over cosine squared x. Run it yourself and make sure you agree. And the reason I say that is it's 1 minus sine squared x. What's 1 minus sine squared x? It's cosine squared x. So this is just 1, okay? And I now have this nifty identity that secant squared x is 1 plus tangent squared x. So we'll just clean this up a little bit. These are the two things I need. Okay, so we're just going to grab the stuff that we need here and move it where we can see it. Okay. Okay, so let's puzzle over this thing here. How do we do this? Well, we just said that secant squared x is 1 plus tan squared x, okay? And we know that the derivative of tan x is secant squared x, okay? So here's what we're going to do. We're going to break this up into two pieces of secant squared x. This is what we're going to aim to make a derivative for tangent out of. But this one here, we're just going to use this identity that we just established here. So now we have tan squared x times 1 plus tan squared x times secant squared x dx. Okay, now we're ready for our substitution. We have here a function of tangent x, okay? So we're going to call u tan of x. Almost put tan squared of x, but that is not right because, come on now. Okay, and then the derivative of tan x, du, is secant squared x. And that's this right here. I've got my full du here. That's perfect. And then f of u is going to be u squared times 1 plus u squared. I can rewrite that as u squared plus u to the fourth. So this is my integral. U squared plus u to the fourth du. That's just u cubed over 3 plus u to the fifth over 5 plus c. Now I'm going to substitute back in tangent for u, and I have tangent cubed x over 3 plus tangent to the 5th x over 5 plus c. Simple as that. This is the same way it worked as before. It just took a little bit of knowledge here about what the derivative of tangent is and what kinds of things are relating secant squared to tangent squared. And as a general note, what I would suggest, if this seemed daunting to you, is just looking at the functions that you have inside here and then finding the things that relate them together, as we did. Okay, so here is a definite integral that's going to use a little bit of trigonometric substitution. Here we have a very clear, function inside a function, and that's ln of the absolute value of cosine x. Now, one thing we might want to do is a little bit of analysis before to kind of see what this is actually going to do. Maybe we can simplify this out. And it's always good to kind of draw pictures if you're unsure. So here we go. I'm going to draw cosine x down here. Okay, and that's all I'm going to draw of it, because the bounds that I have for this integral are 0 to pi over 4. And this over here is one of the zeros of cosine of x. Okay, and that's pi over 2. So what that means is that this function is positive over the integral. Okay, cosine x is positive over 0 to pi over 4. Now the next thing we want to know is, what does ln of absolute value of u look like? If this is u, okay, and this is y, let's just call this equals y. Well, this is ln of x, right? It approaches minus infinity as you get closer to 0. And then it kind of slowly increases to infinity as you go to positive infinity. That's just regular ln of u, but since this is absolute value, what's going to happen is all of the negative values of u here are going to get mapped to the positive side, and you're just going to have a mirror reflection. Okay. Now where you could come into trouble with this function, with that absolute value in there, you could come into trouble if you're going over this period here. So over this little singularity here. But what we're looking at here is we're looking at 0 to pi over 4. And 0 here, 0 is going to give us 1. And pi over 4 is going to give us square root of 2 over 2. So where we're really looking is 1 to square root of 2 over 2 here. And as you can see, these are both on the same side of this function graph. Okay, so we don't actually need, in this case, we don't actually need these absolute value signs. And I'm going to get rid of them right here. Let's just get rid of these bad boys. Let's get rid of that guy. So we're going to replace these with parentheses, and now we can proceed a little bit easier. Now again, we have a function within a function here, and the inside function is cosine. The outside function is ln of u. We need du in order to try to replace this integral, and that's going to be the derivative of cosine, which is minus sine x, and then we need that dx. Now we notice that we have dx here and we have positive sine x here, but we need negative sine x, so we're going to put a minus sign there, and then we're going to take it out of the front of the integral. And I'm going to make some space also so that we can do this cleanly. I'm going to erase some of this analysis. We've figured out what we needed to with that. That was just to decide if we needed two integrals or not, really was the reason we did that. Or actually if this integral was doable. So we're going to rewrite this. we got to keep that minus sign. You'll notice we have the full du now. This and this, minus sine x and dx, make our du. So we can put the du in there. And then we need f of u in here, which is ln of u, but we don't know our bounds. And so let's go down here and do a little bit of scratch. Okay. Remember that for definite integrals, when you're substituting, the bounds are going to be changed. Hang on one second here. Okay, so we've got b here, which is pi over 4. And we're going to need to change that to u of b, which is cosine of pi over 4. And that's, again, square root of 2 over 2. A is 0, so u of a is cosine 0, which is 1. So that gives us these bounds. Now, notice that this is 0.7071, dot, dot, dot. That's less than 1. So one way we can make this easier is by swapping these and putting another negative sign out front. Remember that if you have an integral that looks like this, it's the inverse of an integral that looks like that. So we're going to do that. We're going to switch these and kill that minus sign in front, and here's our final integral. We know this is u ln u minus u from here to here. Let's make some space. Let's make some space. And we now have 1 times ln of 1 minus 1 minus square root of 2 over 2 ln square root of 2 over 2 minus square root of 2 over 2. This is 0, so we can cancel out that whole term. And we now, oh, except this is a positive because it was minus minus. And we now have this. Now, if you want to continue simplifying, ln of the square root of 2 over 2 is actually ln of 2 to the minus 1/2, which is minus 1/2 of ln 2. And we can plug that in here to get something that's a little bit more simple. This is going to be plus square root of 2 over 4 ln of 2, and that is your answer. Okay, so here's another problem. This one is sort of a segue into where we are headed. So this particular derivative will show up quite a bit in what I think a lot of people consider the trickier substitution problems. So this is just kind of an easy segue into kind of the hard stuff. Okay. So here we have tan inverse x, and we have 1 over 1 plus x squared. Now we know this fact, and this is why it's really useful to have just kind of a cheat sheet around of what these trigonometric derivatives, trigonometric identities are, the really popular ones anyway. So we notice that the derivative of inverse tangent x is 1 over 1 plus x squared, and that means that I can call tangent inverse x u. And then if I wanted to find this, it would just be 1 over 1 plus x squared dx. So du, again, is 1 over 1 plus x squared dx. Well, look at this. I have 1 over 1 plus x squared dx right here. So I can rewrite the integral of u du, which of course is just u squared over 2 plus c, and then plugging tan inverse x back in here, we have this. That's as simple as that. Okay, this is another one that you're going to use very frequently. And it's also an example of an integration by parts problem that you can really kind of do both ways. But the way that I like to do integration by parts when I see an x in here is I like to choose that as the function that I differentiate, because it differentiates to be 1. And what that does is it leaves my g prime. Remember, by the way, that integration by parts looks like this. Oh shoot. Kill that guy. Times g prime of x dx. And then you have f of x gx minus g of x f prime of x. And again, you know, sometimes you see this with u's and v's and you have to put dx's at the end and blah blah blah, but it's really not that big of a deal as long as you kind of understand what you're doing. You should be good. So that would leave g prime of x as sine inverse x. And then g of x, well, this is going to be a little bit interesting here. So g of x is the integral of sine inverse x. And we actually did that, I think, during the integration by parts example list. You wind up taking f of x to be, so we're doing, just to be clear, we're doing another integration by parts here. We're doing, let's just divide this off. Now we're looking at the integral of sine inverse x dx. And we're doing this so that we can do this integration by parts. So let's just do this really quickly. Then that leaves g prime as x and f prime as 1 over the square root of 1 minus x squared. So you do need to know that the derivative of arc sine is 1 over 1 minus x squared. And again, there is no difference between arc sine and sine to the inverse. So don't freak out about that. And I screwed this up here. G prime of x is going to be 1 because the product of functions here is 1 times sine inverse x. So this is going to be 1. I kind of gave it away. G of x is going to be x. And so what this is it is sine inverse x, or arc sine of x times x. So I'll go ahead and write that out. Sine inverse of x minus the integral of x over square root of 1 minus x squared. And now we actually have to solve this integral, so we're going to just make some space here. It's going to collapse in a second and it's going to be really relieving, but for now it's just one step right after the other. Okay, so this is actually another example kind of like the one last time where I have a function and I kind of almost have its derivative here. So we have minus 2x dx. The derivative of 1 minus x squared is minus 2x dx. I have some of that. I have x dx, but I could put a minus 2 out here, and then I could do a minus 1/2 out here to sort of cancel those, and that gives me my du here, right? That's my du, see? And I have to keep that minus 1/2, and then this is just 1 over the square root of u, du, right? This is the same thing as saying minus 1/2 times u to the minus 1/2, which is minus 1/2 times u to the positive 1/2 divided by minus 1/2. Well, this cancels with this. Actually, that's positive, so we keep this negative here. We keep the negative, and we have minus u to the 1/2. We plug back in our u, and we get minus square root of 1 minus x squared. And let me just double check that here. Okay, yes, that's correct. So this is the integral. I'm going to leave out my c for a second, okay, because I'm collapsing it up. But if you were just solving this integral, you would want to include that. So here we go. Where did I need this? Well, I needed it right here. So I'm just going to erase this. Okay, I'm going to erase this, and I'll put this minus square root of 1 minus x squared. Again, I'm just putting this up here, and that's going to be x sine inverse x plus square root of 1 minus x squared. Clear some space out. Okay, we scroll back up. Okay, so now I have that integral. And that integral is this beastly looking thing. So this is actually g of x. So we have x sine inverse x plus the square root of 1 minus x squared. We're going to remove this now and make some more space. Okay. Alright, now this part, remember the other side of the integration by parts here, I probably shouldn't have erased that. We take fx times gx, so f of x is x, times g of x, which is this, x sine inverse x plus square root of 1 minus x squared. And then we have minus the integral of g of x times f prime of x. We don't have to worry about this because it's just 1, so we plug in x sine inverse x plus 1 minus x squared quantity square root. Okay, and I'm going to make a lot of space here because we're not quite done. Now, a couple of interesting things about this. This integral here actually appears over here. And what I'm going to do is I'm going to rewrite this. I'm going to go ahead and factor these x's so that I can, it's just kind of housekeeping. This integral breaks up, okay? And I'm going to leave a lot of space here because I'm going to do something in a second. I'm going to actually add this integral to both sides. This integral and this integral are the same. So again, right now I'm just breaking up this integral, so I need another minus. And of course the minus is there because it's in front of this, and I have to distribute that. But what I'm going to do is I'm going to add to both sides x sine inverse x dx. And over here it's just going to make this into a 2 out in front. Okay, and so let's see here. Let's clean this up a little bit more. So now we can kind of get rid of this because we've canceled it out. And I'll bring this in. Okay, and now I've vastly simplified my integral, but now I have this kind of odd thing here, okay? And I need to figure out what this is. Well, one thing that one trick that you'll run into very frequently with these substitutions is that if you have something that looks like this, right? It's a good idea to plug in x equals sine theta, and this is the first one we've experienced with a different order of differentiation. Normally what you try to do is find a derivative inside here. What you're going to do in this case is plug something in for x. So this is another way of saying sine inverse x equals theta, okay? And what we also want to know is what dx is, which is cosine theta d theta, and we're going to plug this in where we see dx, and then we're going to plug sine theta in where we see x. So here we go. We have the integral of 1 minus sine squared theta d theta. Excuse me, this is dx. I've not yet plugged in d theta, or what I need to for dx. I need all of this, because I have a dx over here, so I need all of that. I need cosine theta d theta. Okay, I'll erase this here. This, of course, is, we know that cosine squared theta plus sine squared theta is 1. So 1 minus sine squared theta is just cos squared theta, right? We're just moving this to the other side. So we can change this to cos squared theta. And what's the square root of a square? Well, it's just cos theta cos theta. So we've managed to boil it down to cosine squared theta. Okay? Here we go. So this is the integral of cosine squared theta d theta. And a quick way to find that integral, if you can't remember, we do know that cos squared plus sine squared is 1. And I'm spacing this out for good reason. We also know that cos squared minus sine squared equals cosine of 2 theta. Okay, that's from the double angle formula, which is also from the addition law of cosine, or whatever it's called. Sum of angles rule, I think. Now, if you integrate both of these, okay, then we have theta up here, and we have 1/2 sine 2 theta down here. Okay? And if we add these two together, what we get is, we get 2 times the integral of cos squared theta d theta is just theta plus 1/2 sine 2 theta. This is maybe a harder problem, I guess. Bring that 1/2 onto both sides. Now the last thing we have to do here is we have this, okay, so we can just take this and set it up there because that's our answer, and we can clear some more space out. And now we're going to try to telescope this back. A lot of work on this problem here so far. Okay, what we have to do now is we have to plug in what we had for theta. So we had that x was sine theta. That's how we started solving this, which means that theta is sine inverse of x. Okay, so when we rewrite this, we're going to have 1/2 sine inverse of x, and then we're going to have plus 1/2 or 1/4 sine 2 of sine inverse of x. Well, that's kind of creepy. How the hell do we find that? Yet another step. This might be one of the longest problems I've done yet, and hopefully I didn't make a careless mistake somewhere. Sine of 2 theta, okay, and maybe that's a bad variable to use. I'm just trying to create another determinant, okay. Let's say sine theta of z, I don't know. There's an addition formula for sine, which goes like this. When they're both the same, it looks like this. Okay, so it's called the double angle formula for sine. And it's just that right there. It's pretty easy, okay? So what we can say, and this is just scratch here, is that 2 sine inverse of x is going to be 2 sine of sine inverse of x times cosine of sine inverse of x. Now, there's a couple of things you'll have to know in order to do this. Not only the fact that this is true, or that cosine squared plus sine squared is 1, or any of the rest of the stuff, which goes back to this original point that it's really good to have a cheat sheet of these freaking trigonometric identities and derivatives, etc. if you're going to be doing this, because you will get lost if you don't know it. You're going to need to know that the inverse of a function, the function of the inverse of that function just gives you x. That's the first thing you're going to need to know. The second thing you're going to need to know is that this right here, this term right here, winds up being the square root of 1 minus x squared. Okay. And so we can rewrite this, good God, as this right here. Now remember, we have a 2 in front of this, which is going to cancel with this 4 eventually, but I'm not going to scare the shit out of you just yet. Over 4, these two things can cancel. Okay, we will need to do that now because we're about to get back into the thick of it. Okay, 1/2 here. Okay, so this is this integral here. Now, where did I leave off? I left off with everything except for that. Okay, so we're going to just clear all of this crap out. You'd probably want to do all this work off to the side or something before, you know, show your work or whatever. And this is the integral we are replacing. Oh, that doesn't quite do it. Well, I'm gonna have to take the top part of that too, unfortunately. Not rewriting all that shit. Okay, here we go. And then I'll just kill that bad blah. Okay. Alright, so here is what, good God, look at this thing, Jesus. Okay, so here's what we've got, alright, and we subtracted this, so we're actually going to have a minus sign here. Okay. That little minus sign would be distributed across this. Remember, this was 1/2, and this was plus 1/4. Well, if I have a minus sign, it's going to be minus and minus, right? So this is a minus sign as well. And we can do some simplification. Notice that these two terms are the same. So what I can say is this is 1/2 x times the square root of 1 minus x squared. And then I have plus x squared minus 1/2 sine inverse x plus c. And that should be close enough. What the hell did I just do? There we go. That should be close. I'm going to double check it, but I think that's it. Okay. Just as a note, this is 100% one that I would double check on Wolfram Alpha. This is a pain in the spankus. Oh, actually, look at this. It looks like I missed. Looks like I actually missed one. I think I had to divide off this 1/2. So yeah, I did screw this up. You're going to want to multiply both sides by 1/2. And here we go. So this is going to be 1/2 of all of this. Okay. So something like this. X over 4 plus 1/2 okay. Let's run over these really quick. Nice morning exercise. So this little thing right here, this is going to play a role sort of as the last integral did. Maybe one thing that you've noticed, maybe I should just say this. Sometimes you're going to have things that look like this. Yeah. There's a better way to write this. I'm going to use u because that's kind of how we've been writing it. U prime f of u du, and the whole, or dx, excuse me, and the whole point is to combine these and make du and turn this into f of u du, right? Well, there's another way to do this, right? You could see this goes both ways. So if you want to say instead of u equals some u of x, right? If you want to say x equals some phi of u, right, then you can define dx as phi prime of u du and shove that in where you see dx. So for instance, if you had u if you had really any f of x, right, dx, it's the same thing as f of phi of u times phi prime of u du. If you look at this and this, you'll see that it's the same thing, what I'm saying. But anyway, the reason I kind of go off on that tangent is this is one of the ones where we're going the other direction. Okay? And when you see this little guy right here, this square root of, I'm going to be general here, square root of b squared minus a squared, what you want to do is you want to try the substitution a equals b sine theta. Okay? And you can remember this because this is similar to the derivative of arc sine theta. Okay, or arc sine x. And we are going to use a little bit of trigonometric just facts about this here in a minute. So there is some trigonometry coming. I don't know why I'm having such a hard time with that word today. Okay, so we're going to say that x equals b squared, in this case would be 9, so we're going to use 3 sine theta. Okay. Dx is then going to be 3 cos theta. Okay. And we're going to just plug this into, I'm sorry, and there's a d theta there as well. So we're just going to plug this into the integral, just like I was saying before. For dx, right, for that term, I'm going to actually plug in this whole beast right here, 3 cos theta d theta. Then on the bottom here, I've got, what do I have? I have x squared, that's 3 sine squared, so that's 3 squared sine squared theta. And then in here I have the square root of 9 minus 3 squared sine squared, which is 9 sine squared theta. I can do some canceling, and I'm going to bring the 3 out of here, so I'm going to bring the 3 out of here and leave that as 1, and that as 1, and I'm going to bring the 1/9 out in front of the integral. So now we have cosine theta d theta over sine squared theta, and then what do we have here? We've got the square root of 1 minus sine squared. Well, that's the square root of cosine squared, so that's cosine squared, or just cosine, excuse me. So these two are going to cancel. So you see how if you kind of are okay with your trigonometry, this is pretty damn easy. If you're not okay with it, it's probably not very easy. It's just an unfortunate fact. And that's why I keep saying, if you've been watching these videos or paying attention at all, that it really helps if you just have a cheat sheet of trigonometric identities and trigonometric derivatives. Okay, so now what is this? This is 1/9 times the integral of cosecant squared theta. Now, suppose I don't know what this is, okay? But I do remember, because we did this the other day, that the derivative of tangent is secant squared. So I'm kind of like, well, I wonder if I do cotangent, if that gives me cosecant, you know? So let's give it a shot. Let's take the derivative of cotangent x. Okay, well, that's the derivative of not sine over cosine, but cosine over sine, right? And I just use my quotient rule, square the bottom, then take the derivative of the top times the bottom, which is just minus sine x times sine x. Then take the derivative of the bottom, we have to put a minus sign in there, take the derivative of the bottom times the top. So that's minus cos x, cos x. So here we have minus sine squared x plus cosine squared x divided by sine squared x. These just cancel to be 1, and we have minus 1 over sine squared x, which is minus cosecant x. So again, know your trigonometric identities, and you might not even need to know your trigonometric derivatives. It's squared. Boop. This, you see the similarity here. What did I just do? I just took the derivative of cotangent, and it was negative, so I have minus 1/9 of the cotangent of theta plus c. Now here's the issue. There's a few ways you can go about it from here. You can go back to theta, and you could say, hey Lincoln, theta is just x over 3 inside sine inverse, right? You could do that. But there's a better way. There's a much better way. Okay? Let's think about triangles for a second. I'm going to say this is x equals 3 sine theta. I'm just literally writing this down. What I'm going to do is I'm going to divide out this 3. Okay? And I'm going to get rid of it because we're about to do some talking. Okay? So, how do I find the sine of theta? Well, the sine of theta is just the opposite over the hypotenuse. So here it's going to be x over 3. And then what's this sine here? What's this side here? Well, square root of 9 minus x squared. Alright, now what is the cotangent in this case? Well, it's going to be the adjacent side, which is this, divided by x. It's that easy. What's the adjacent side over the opposite side? That's the definition of cotangent. The adjacent side is 9 minus x squared. The opposite side is x plus c. You're done. Boom. Okay, for the last integral, I'm going to go ahead and do something that's a little bit different. I'm going to take the same integral and I'm going to do it like 3 or 4 times. And I'm going to do it a different way each time. And the reason to do this is, I want to show you that, Calculus 2, which is different from Calculus 1, in the sense that it has a lot to do with kind of trickiness and creativity of these integrals. And, honest to God, the integrals you might encounter are not even going to be really that difficult, more than likely. The difference maker for you, if you really want to succeed, is algebra and trigonometry. And maybe you've gotten that sense already, but the better you are with those, the better you are going to be with this. And so I'm going to show you an integral here that looks kind of complicated, and then at the end we're just going to look at how much calculus we actually did, and what amount of it was algebra. So here I'm going to look at, I'm going to call f of x 1 plus e to the x. Now if I tool around with this for a while, I can actually find that f prime of x is minus e to the x over 1 plus e to the x squared. Now I know that f squared of e to the x, I could just multiply both sides by 1 plus e to the x, both the top and bottom, numerator and denominator. And then I notice that this right here is just, it's just the minus, the negative form of if I took, oh, I'm sorry. Hang on, I've got to back up for a second because I made a decent mathematical error here. This is another way to write f of x. All I did was take f of x and multiply both the numerator and denominator by 1 plus e to the x. F squared of x is going to be 1 over 1 plus e to the x, quantity squared. Okay? So what we really want to do is subtract f squared from f. Okay, so we have f minus f squared, and then it's the inverse of that, so we have f of x squared minus f of x. That's my f prime. Now I can factor this. Okay? And now I have this interesting functional equation that says that f of x is just its own derivative divided by f of x minus 1. Okay? Now, I can look at this integral I have here. Alright? I'm calling this the integral of f of x. So it's the same thing. I haven't broken any rules. There aren't any discontinuities over the real line of f of x. So I have f prime. In fact, this function is ultra continuous. Okay, I now have this integral. Well, now I can perform a u substitution. I'm going to put my equal sign over here, and I'm going to just say u is going to be f of x minus 1. du is going to be f prime of x dx. b is going to be infinity, which is going to go to u of b, which is 1 over 1 plus e to the x. Going to infinity is going to be 0, so minus 1 is going to be minus 1. 1 over 1 plus x to the infinity. Yeah, that's 0. Minus 1 is minus 1. So a is going to be 0. U of a is going to go to 1 over 1 plus e to the x. That's 1 over 1 plus 1, so that's 1 half. Minus 1 is minus 1 half. Okay? And maybe the way we need to be doing this yeah, we'll just continue. Okay. So, here we have this weird integral. Minus 1 to minus a half of 1 over u. Well, how do we get this? Because we're going to have logarithms that look like this. That's not cool, right? So what do? Well, we're going to take the integral of this, but what we're going to do is we're going to use ln of u, okay? The absolute value. So here we have 0, right? Because ln of 1, maybe I should write this whole thing out. To have ln of 1 minus ln of minus 1 half. I could have made a substitution to make these all positive, and kind of thinking maybe I should, but that's okay. We're going to do this like 3 different ways, so buckle up. So this is going to be minus ln of a half, which is minus ln, this is so complicated, minus ln of 2, which is just ln of 2. That's the right answer. Okay, we're going to pause it for a second, and then we're going to try the next way. Okay, so the way that we're going to do this is with a u substitution. We're going to say that u is e to the x, and du is e to the x dx. Okay, and we're going to play around with this for just a little bit to make sure that we kind of know how we're building this. So what is this going to look like? Well, first of all, we need to pull a du out. Right, so what that gives me here, I'm just going to write out here's what I have. Okay, I need to pull the du out. So what's that's going to do is going to, I'm going to switch my variables up here, and I don't want to do that. I need to have an e to the minus x out here. Okay, so what I'm doing, I've got something like this. This is going to become my du, right? So I'm going to be left with this. Okay, and I can rewrite that. This is going to be 1 over e to the x times 1 over 1 plus e to the x. Right? And then I've got my du over here. Okay, so here we go. The other thing I need to know is what's going to happen to my bounds. U of b is going to be u of infinity. That's going to stay right at infinity. U of a, that's going to be e to the 0, which is going to be 1. So we have infinity, we have 1. Okay? And we have 1 over u times 1 over u plus 1 du. Now one thing we can do here is we can split this up into what's called, using what is called the partial fractions method. I might do a separate video on that at some point. But it's pretty simple. Basically all you're doing is you're saying, okay, I have this kind of product, and I know I can break it out into two different fractions. Sorry, that should have an a on top, where these are, a and b are some kind of forms that are simpler than u and u plus 1. So what I do is I just multiply both sides by u times u plus 1, and this whole equation becomes 1 equals u plus 1 quantity times a plus u times b. And I can simplify that to be au plus bu plus a. Now, and that equals 1. What I notice about this is there's actually two equations inside of this. First of all, there's no u's. If there were some u's on this side, okay, on the left side, then I would have a plus b equals something. But instead I get a plus b equals 0, because there's some over here, there's none over here. So there's 0 over here, which means whatever over here has to be equal to 0. The next thing I get is that a equals 1. And these two together mean that b has to equal minus 1. So I can rewrite this integral as a being 1, so that's 1 over u, minus 1 over u plus 1. Okay. Now, here's what I'm going to get when I integrate this. I get something that looks like ln of u minus ln u plus 1. Integral, so we're going from infinity, or 1 to infinity. Now there's a couple of ways to look at this. The way I like to look at it is I like to go ahead and bring this back in to ln. Okay, because it makes this first limit that we're going to do a little bit easier to understand. As we go to infinity, right, and I'm just using, again, a property of the logarithm to bring these back together. As we go to infinity, this is going to look more and more like 1. Okay, so we're going to have 0 here. As we go to 1, we could just plug in 1 for u. So that's 1 over 1 plus 1. That's just 1/2. And this is ln of u. Because this is minus ln of 2. Did I say u? I meant 2. ln of 2. This is minus ln of 2. We have a minus sign there. So we get that. Okay, so I'm going to do the same integral again. I'm just going to use a different algebraic manipulation. And again, this is not to scare you with things you might not have thought of. It's just to say that, you know, everybody kind of thinks of this stuff in different ways. And it's a lot more about algebra than it is calculus. The calculus you wind up doing should be so easy that it's second nature, but this is the algebra that you kind of have to tweak with. Now look at this for a second. What do I see here? Well, I see a form on the bottom, and I see something that's really close to its derivative up here. All I did was multiply both sides by e to the minus x. So here we go. We're going to rewrite this as e to the minus x over e to the minus x plus 1 dx. Well, now I'm going to try this u substitution, where I have u at e to the minus x plus 1. That's not very clean. E to the minus x plus 1. And I have du, which is just the derivative of this, which is just minus e to the minus x dx. Well, I've got most of that here, but I am missing my minus sign, right? And then I need to know what happens to my bounds. B is infinity. That's going to go to u of b, which is e to the minus infinity. What the hell is that? Plus 1. It's e, sorry. And that's just 0 plus 1. So this becomes 1. A is 0. Well, that's going to be u of 0, which is e to the 0 plus 1. Well, that's just 2. Got to keep my minus sign here. Then I've got my du on top. That was this quantity here. Okay. And then I've got u on the bottom. But look at this. I've got a negative sign in front, and I've got swapped bounds of integration. So I can get rid of that negative sign and the swapped bounds of integration in one foul swoop. Okay, now I'm ready to integrate. That's just ln u from 2 to 1. Guess what that is? It's just ln of 2. There you go.